Okay, so here we have just our wee bit of review. The prophase, and I really love these pictures because they show not only kind of an artist depiction of what's going on, but then it does a comparative of the actual cell, which is really pretty cool. When you guys get more into like laboratory procedures next term, and you guys get into clinical pathology, some of the big tests that you as technicians are going to be looking at are the form of these epithelial cells. They can really tell you a lot of information. We can see how many of them are actively dividing. We can see what stage are they in. We can see and tell just a whole host of information. So here we have prophase, the P in our PMAT. And here we can see that all of our chromosomes are still locked inside the nucleus. And what we need to do is set them free. So the nuclear envelope is going to dissolve. And here we have our centrioles, which is the organelle. And these are going to start to get organized and start doing their thing. Here we had our metaphase. Move you guys up here. Oh, that's much better now. It's the one thing I do love is instead of only seeing like 4 of you when I'm in the classroom, I can see everybody. All right, so here we have the metaphase, middle. So our nuclear envelope is gone, and our centrioles have formed their little fibers and attached to the centromere, these little center dots, and lined the chromosomes up in the middle. And this is a fabulous picture right here because you can, in fact, see, if you look really closely, this dark line here are the chromosomes. But if you look at these little light purple, you can see the fibers that have attached and lined them up. That's pretty fabulous. All right, now we're into the last two. And remember, I did mention that I do have, I think I have them on the Moodle. I know for a fact that if you go to my website, if you're like, I don't remember where that video was, if you go onto the website, I have, if you do the drop-down little menu, I have a whole little drop-down called Helpful Videos. And I have both of the videos, the Amoeba Sisters and the animation linked to my website. So you can go back, and I suggest that you rewatch them just to get it clear in your head. Now, as I said yesterday, on your test on Monday, I am not going to have you identify photos. I'm not going to have like a picture of anaphase and ask you what stage is this cell in. The way I'm going to test you over these cell phases is I will ask, what is happening during such and such a phase, or this is happening, what phase is this cell in? And so it will be multiple choice and make it a little bit easier. So here we have anaphase. Oh, I did shrink this picture down, but you can kind of still see. In fact, there we go. During anaphase, we've now taken the spindle fibers from the centrioles, and we've started pulling those chromosomes apart because each half of the chromosome is a complete section of DNA. And so what I need to do is one section completed needs to go to one side, and one section needs to go to the other side, so that each new, or the old cell and the new cell, each have their own complete DNA. And so that's what's happening during anaphase. We have this, it's also a tug of war as well as a push of war, like a tug of war and a push, because the spindle fibers are pulling them apart, tug of war. And then we have these proteins on the inside, push of war. And here again, you can see an actual epithelial cell. And this is really a pretty remarkable picture because you can see here, and I don't know, you guys can see my little hand on my screen, but here we have the complete set of DNA, and here we have the other complete set that are now being pushed and pulled towards the poles or the different sides of the cell. So that's what's happening during anaphase. Our fibers are separating the chromosomes. And then our final phase is telophase. Our chromosomes have now been pulled apart. We start to get what's called,
can you go back so I could take a picture of that,
of course
please?
I can, absolutely. I will mark Carol present while you are doing that.
Thank you. The slide that we have, it doesn't, that's covering the majority of what's available.
That's right. That's right. I had to resize the picture. I did resize. So there you go.
Thank you.
During the final, so you're very welcome. During the final stage, we are now nearly completed. We've formed what's called the cleavage. It's kind of a funny word for a cell, but we have our cellular cleavage. And this is just where we get the little divot where we can now form a new line of the bilayer and actively separate the cells. And the other thing that's happening during telophase is we now have our DNA, a complete set on one side, a complete set on the other side, and now we need to recontain it inside a nucleus. So that's the other thing that's going to happen. We have our cleft. We're going to start building our new cellular membrane, and the nucleus starts to reappear. So that huzzah, you can see here, this little guy, we've already formed our cell membrane, and we now have a perfect daughter replication of our parent cell. These cells will now enter, this is hard to say, interface, enter, because unless the body says, yes, we need you to keep dividing, they're just going to go into their interphase. Now, if the body says, yes, we do need to keep dividing, that interphase period will be relatively short because they will immediately start preparing to go both cells into mitosis. So now the first cell can become a parent again, and the daughter cell herself can become a parent. And so if the body says, yeah, keep dividing, we still need some, they will immediately start growing, duplicating their organelles, duplicating the DNA, entering mitosis, prophase, dissolving the nucleus, getting the centrioles organized, metaphase, spindle fibers attaching to the centrioles, lining them up in the middle. Anaphase, push-pull apart to the opposite poles of the cell. Telophase, reform the nucleus, separate the cells. And then, second verse, same as the first. And we just keep going.
Mitosis, that takes place like within seconds, right? Or is it like?
Yeah, it's very, very quick. It kind of depends on the cell. But yeah, this is not like an hour-long process. This is happening very, very, very quickly. I honestly don't have the exact timing of how long the process takes. I know it does depend a little bit on the individual cell. In these slides, we're specifically looking at epithelial cell, and this can happen, I don't want to say instantaneously, but within seconds, you can have one cell dividing into two.
Okay, thank you.
You're welcome. Here's another fabulous. Oh, go ahead.
I had a quick question. So in interphase, so for example, now the cells have separated, but then the daughter cell still has to create new organelles, correct? Would that be interphase?
So if you remember during interphase, the preparation, the single cell has duplicated not only the DNA, but has also increased the number of organelles. So that's all happening during interphase, the preparation phase. So by the time we get to mitosis, we'll have two complete sets of DNA and we have two complete sets of organelles. The only thing that we need to do during mitosis is separate the chromosomes and separate the cells.
During this entire time, the chromosomes were supercoiled.
Mhm.
Is that right?
Yes, that's correct.
So, it's during telophase that they're becoming no longer supercoiled?
Yeah, they would begin to well, not completely uncoil, but achieve more of that double helix that we're used to seeing. And then when the cell enters interphase, so we have interphase, which is the preparation, but the interphase part, in fact, I think I have, let me look. Let me go back, hang on one second, right here. So our interphase, this is where we have the different phases of interphase. We have the, so here's the beginning of interphase. I'm just hanging out, being a cell. Then we enter, oh my goodness, I need to start preparing to divide. So I'm gonna grow. Then I replicate my DNA. Then I get ready to divide. I pack my lunch. Then I go through active division. And immediately after active division, I can either start growing again, or I can stop and just do my little cell job. Still interphase, because remember, interphase was also known as metabolic, meaning I'm just a cell, I'm doing my job, I'm just not getting ready to or actively dividing. So if I'm preparing or even not preparing, those are both considered interphase. So it is during telophase that now we've reformed the nuclear envelope and the supercoiled DNA can uncoil and form that double helix that we're all used to seeing. And then we can either just go about our cell business, or we can start replicating that DNA again using the leading and lagging strand that we discussed. So this is just another picture for my adorable little visual learners. You know that I am insanely visual, and pictures, I need to see it. I need to see it in my brain. I can't just look at words on a screen. In fact, it drives poor Mr. Hamilton crazy, because when he and I are working on the term academic schedules, he's very, very analytical. He is a word number thinking person. So he will have this like Excel spreadsheet. I can't see it. I can't do it. I need to have like blocks, and I need to do it like a Rubik's Cube, and it drives him insane because he can't see my method. So we work really well together because we have two completely different methods that end up with the same result. Yeah, it happens so fast. I mean, it's taken us 2 days to discuss interphase through mitosis, but this is happening almost instantaneously. So here we have, now this is thrown in a new one. We don't have to worry about this one. We're just doing the main phases of mitosis. But here we can see, once again, I'll just review. Here's our cell prophase. Our DNA has already been replicated. We have dissolved the nucleus, and our centrioles are getting organized. Metaphase, this is a fabulous picture. Let me blow this up a little bit. Here's our chromosomes that are lined up in the middle. And in here, you can see this dark spot here and this dark spot here. Those are the centrioles. And you can even kind of see very faint little purple lines of the spindle fibers. You can see the fibers. Here we have our anaphase, where again, if you look in the middle, you can see the fibers and the proteins that are pushing, and then you can see here we've almost gotten it all the way to the centrioles pulling, and we have divided and dispersed our DNA. And then here we have the reforming of our nucleus. It's not quite finished yet, that's okay, but you can also see this very faint line in between That is the reconstruction of the bilayer to separate the two cells. I love these pictures. I love them. And then here you can see in more of a cartoon what is happening. So I love this picture because it really does. And these are real cells. These are real cells that are happening. So how does all of this get controlled? Because we don't want just uncontrolled growth. That would be super bad. In fact, there's a disease that you have uncontrolled skin epithelial cells. It's actually considered to be a very rare form of cancer. Cancer really just is when our cells go rogue and they are like, we don't want to behave like regular cells. And something happens to their DNA and then they start replicating incorrect cells. How can these tumors get so big so quickly is the control of the division. So our body right now is governing what cells should be dividing and what cells should just be working as regular cells. What we have there is the word I was trying to remember, Douglas was trying to remember yesterday, contact inhibition. Inhibition to stop. So I gave the example yesterday, if I was on the stage and I was a cell and my body said, oh no, we are low on Huff cells. We should probably start dividing and making new Huff cells. And it says, as soon as Huff cells fill up the whole stage, then we can stop making Huff cells. And so as I'm making Huff cells, once the stage is full and I am side to side, front to back with Huff cells, I am now in contact with other cells. That's my signal to stop. That's why it's called contact inhibition. When that cell comes in contact with all the other cells, they're told to stop dividing. And that's what stops it. Now there's a disease, really quite fascinating. House, I told you I finally finished, but I was in the midst of a terrible House binge. There's actually an episode on House where you have uncontrolled epithelial division. And the other problem is that as the cells are dividing, the DNA has been messed up and now it's dividing into incorrect cells. Now the problem with this disease, it's really fascinating, is that my skin is lovely and soft and pliable and elastic. I can pull it, I can bend it, and I can shed it. So as the new cells are coming up, I'm shedding off the old cells. Again, a little bit of Huff for everybody. What happens in this disease is that the cells don't shed, and something in the DNA tells them to add a substance called keratin, which is part of your fingernails. And these people end up with these giant tumors that look like tree bark. And they end up looking like a tree person. The skin on their hands starts growing into branches. The skin on their feet starts growing into branches. They get these huge tree bark tumors on their face and their body. And they start turning into, I think if you can probably just Google image search tree people disease, you'll be able to see just on the outside what happens if we have no control of this cell division. It's a really fascinating rabbit hole to go down. It's a terrible, terrible disease. There's no known cure other than, chop off the tumors and wait for them to come back. But it is kind of a tangible thing that you can see as far as what happens if we have uncontrolled cell division. So this is a slide that, oh yes, Sean, there is also Cells at Work, which is a really cute cartoon. And it's really, really cute. And it has so many different episodes. And so that's another one. Great recommendation, Sean. I know it. Yes, I've seen it. It's wonderful.
In Hawaii, there was this homeless guy who had like his whole arm was like white and it like looked like rocks, like what's that disease from Game of Thrones?
Oh, grayscale.
Yeah, so kind of looked like that. I wonder if it's similar. Like, I don't know if that's a real
I don't know if it's similar. I know that you're not born with the tree person disease. What usually happens is it's caused by, we think, the infiltration of a certain type of bacteria. So what can happen is you get a little cut on your foot. If you've gone barefoot, you get a little cut on your foot, and this bacteria infiltrates, and it's what messes up the DNA. But the problem is that then we have this cascade effect where now you have the bacteria in the body just causing shenanigans, and all of the cells that it touches starts replicating incorrectly. And it's crazy. So I'm sad to say, Leanna, I am not a secret weeb. I don't know what a weeb is. It does not sound good. I don't know what that is. The only anime I've ever really seen is the anatomy cartoons. And I didn't
I've got
even
a
know that
question.
was classified as anime. Charles, yes, what can I answer for you?
Okay, is that why the tree people, like, I've looked at pictures before, is that more prone in third world countries?
Yes, it is more prone in poorer countries where the hygiene is not the best, the environment is contaminated, people are not wearing protective equipment like shoes. So it's not so much that them as a population are more susceptible, it is that their environment is more inviting to this specific type of bacteria. And so that's exactly why we see it in certain environments. You're not probably not all that likely to develop it like in downtown Houston. So you can probably, I wouldn't take your shoes off in downtown Houston, but you can and not worry about getting this bacteria, not this bacteria. You can get a million other bacterias. So this protein synthesis, okay, it's a derogatory. Oh, yeah, so I am not. I don't watch anime on a regular basis. I liked the animations because a student previously, just like Sean did, recommended it. And so I wanted to go in because anything you guys recommend to me that could be beneficial for the class, I go in and I look and I watch. And if I think it's amazing, maybe I'll even link it to my website. There were just, for those ones, there were so many, I couldn't link them all to the website and I wanted them all. So it's amazing. So how do we create the proteins? Well, guys, this is, if you look at this, don't we see some words on here that we already know? We do. I know some of you are like, I've never seen those words ever before in my entire life. That's how sometimes students sound to me in my head. No, you have. We talked about this quite a bit. How do we create new proteins to compensate for new cells? How do we create these proteins that is going to facilitate the division and give us everything that we need, give us the proteins and the energy? We have to create them. And the way that we create them is how we write it down. We write down what we need. What protein do we need to make today? Today for dinner, boys and girls, Miss Huff is making her her house famous spaghetti. It can't be world famous because none of you know about it, but it is famous in my house. So the protein that I need to make today is spaghetti. The first thing that I need to do to make my spaghetti is I need to write down the ingredients, because maybe I want one of you to make it. So I'm going to write it down. I'm going to transcribe. Yes, I've heard that I am the Miss Frizzle. I've had people buy me the books and I love it. I love being compared to her. I think she's fabulous. So I make homemade, of course I make homemade sauce, Nathan. Do you think I'm a heathen? Come on. Not only do I make homemade sauce, but I reduce it for over an hour so it's super, super thick. And then we use it for sloppy joes the next day. So, so I'm going to transcribe it. And then I have, so now I have tRNA. Then I send it out mRNA. So I'm going to send my recipe out to you. And you're going to get that. You are now represented by a ribosome. And you're going to translate it. And you are then going to make the spaghetti. That is everything we just already talked about. Yes, Charles, and I bought my red wine. I like to use a nice bold Cabernet. Gives it a nice kind of rich, thick flavor. So don't you test me on my spaghetti making skills, because I got some skills. I'm just saying, Charles, trying to trip me up. No, oh. Anyway, so all of this you can see is just what we've talked about previously. The 3 steps, the 3 types of RNA to make a new protein. Now, what happens when things go horribly, horribly wrong? We get a genetic error. So Charles is just very serious about his spaghetti, and he wants to ensure that I am making it correctly. And I appreciate that. I do. And I did buy a lovely, it's not inexpensive. I don't have expensive tastes. I'm not a big wine drinker. I like a glass every now and then. I get the cheap stuff. I like Barefoot. It's not expensive and they make a decent wine. So I did get a nice Barefoot Cabernet to put into my sauce this evening. So I to drink, I would prefer a blue soda. But for cooking and every now and then I will have it. It makes me feel fancy to drink out of a wine glass. I feel fancy. We're not, Deanna, gonna go into too much as far as genetic mutations, as far as apoptosis and mutations. We're just gonna basically just get the foundational concept. We know that a mutation is any time the DNA is incorrect. And then the cells that are replicating are also replicating incorrectly. This can happen during either mitosis, which the end result would be a tumor, either a malignant tumor, which would be cancer, or a benign tumor, which would be not cancer, but both are in fact a mutation. A benign tumor is simply the cells are replicating. Now the DNA has not changed. Okay, they are still, usually let's take a lipoma. Lipo meaning fat, oma, tumor. And so these are fatty tumors. You can get them anywhere. Dogs get them. You're still making fat cells, okay? That didn't change, but the problem is that nothing is telling them to turn off. We don't have that contact inhibition. We develop a tumor, but because the DNA hasn't changed and it's still functioning as it should as a regular cell, we say that it is benign. It is not cancer. Malignant tumor is not good. That means cancer. And that means that something has happened in the DNA, so that cell is no longer functioning as it should. So let's take a liver cell, for example, since we were talking about wine and beer, let's talk about our livers. If you have a liver cell go, I don't want to be a liver cell anymore, and changes the DNA. Now, obviously, is it changing its own DNA? No, something has happened. But now it's not functioning as a liver cell. And now it is dividing and creating more cells that don't function as liver cells. But here's the problem. Contact inhibition does not apply because these little cells never come in contact with each other. They continue to divide until they take over the liver. Then they will migrate to other parts of the body, and you get uncontrolled tumor growth. So that would be a mitosis mutation. But you can also have meiosis. Remember, meiosis is the reproduction. Now, meiosis is not an exact copy. Meiosis is where you get some genes from your mom, some genes from your dad, bippity boppity boop, you. But what happens if one of the DNA sequences from either mom or dad got messed up? And that happened to be the sequence that bippity boppity boo turned into you. Now you can have some pretty significant genetic mutations. This is different than the cancers, the mitosis. It's important to know your genetic mutations and your mitotic mutations are two different mutations. Same idea, we have incorrect cells reproducing, but the outcome is different. So how can we get mutations, either genetic or mitotic? Well, virus. In fact, we're dealing, I don't know if any of you have watched the news lately, but there's this virus called COVID. It's a corona, I don't know if any of you have heard about this. It's really quite terrifying. Of course you've heard about it. I'm joking, of course. Yeah, news to Charles. We have this virus called COVID, and one of the dangers is that COVID, so the symptoms of COVID are not because of the virus itself. The virus is not causing you to have symptoms. Your body reacting to the virus is what's causing the symptoms. So when the virus gets into your lungs and your lungs go stranger danger and starts producing mucus, remember I did the little stuck in the wall, mucus is formed. And your cilia crowd surf that stuck virus. But the problem is that the virus overwhelms and your lungs start to produce more and more and more fluid. And the problem is now that you can't evacuate it fast enough. Lung tissue is very porous because of, our goblet cells, very nice, Risa. Our goblet cells are what's producing the mucus. But now we're producing it faster, and our lungs are really porous. They're like a big sea sponge with these really big voids. And those voids fill up with fluid. Well, everything that's filled with fluid can no longer have gas exchange. So now you are not getting the oxygen that you need. Now your body is in a whole different series of a world of hurt. Now, the thing is about COVID that is a little bit terrifying is that we know so little about it. We do know that the virus itself can mutate, which is terrifying. Because what essentially is happening, exactly the same. Now, obviously, do viruses have DNA? No. However, they can replicate. But what can happen is similar to our mutations that we've just talked about, our genetic or our mitotic mutations, the virus can go, okay, I see what you all are doing out here. You're starting to get drugs that kill off my people. You are starting to get a vaccine that teaches your body how to fight me, and I'm not happy about that. So you know what I'm going to do? I'm a virus. I can do whatever I want. So I'm just going to change, and I'm going to change the protein on the outside of me so that your drugs don't work and your your vaccines don't work because your body doesn't recognize me now. And that's where you start hearing about all these different strains. And this is where mutations, either cellular or non-cellular, you can hear it in my voice. I get a little excited talking about this because I find it really, really interesting. So the virus is not replicating an incorrect DNA like a cellular mutation. What the virus is doing is changing the protein on the outside of the cell. Remember, we talked about our immune system going stranger danger, stranger danger. How do they know it's stranger danger? They're identifying it by the protein. So if I have a list of stranger dangers and that virus changes, he goes and has plastic surgery and changes the way he looks, I don't get stranger danger anymore. So there you go. But the other thing that we're not really sure of with this particular virus, we know it happens with a lot of other viruses, is viruses can get into and hide inside your cells, and then they just start messing up your DNA sequences inside the cells. They just start going in and start unplugging and replugging stuff. And then that cell, as it goes through its own division, is now replicating an incorrect DNA sequence. So viruses, super scary. Radiation can also get into your cells and start messing up your DNA sequence. Now, radiation is super scary because you can be affected personally. Like think there was a fabulous, if you have, oh my goodness, what is happening in the chat right now? Okay, we're done talking about the goblet cells. If I'm not allowed to talk about it, you're not allowed to talk about it. Charles. Oh, it was Nathan. I'm sorry, Charles. You know what? I just yelled Charles because it's usually Charles. It's usually Charles, but you know what, Nathan? I said no. I'm sorry, Charles. I apologize.
I didn't even bring it up.
Although I'm going to say, Charles, you're going to do something that deserves me yelling Charles at some point. So there's, you got a freebie. Oh, that's funny.
It's always Nathan's fault. It's okay.
Yeah, so it's going to be one of the two. All right, so radiation, going back to that for a second. So radiation can hurt you. So if you absorb a large amount of radiation, that radiation infiltrates your cells, messes up your DNA, gives you cancer. Bam. But the other terrifying thing about radiation is that it can get into your reproductive cells and start messing up that DNA, meaning that you start passing on to your successors, your children. And because your children were spawned, yeah, I'm going to use the word spawn. Children get spawned because they are kind of like little demons. Your children were spawned with messed up DNA. Guess what happens to their children? Messed up DNA and their children. And you can have successive populations in the family. And then certain chemicals can cause genetic mutations. Things like certain chemotherapies, certain medications can cause a mutation in the cells. Now, the picture I'm going to show you are genetic mutations, not mitotic mutations. However, they're a lot more fun to look at than mitotic, because mitosis, all you're going to see is a cell replicating. We can't really look at the DNA of that incorrect cell. Right here, this is the heart of my heart. You have heard me talk about Bentley. He was my soulmate. He was the dog I will never get over. He was my buddy. I loved him more than any, oh, shouldn't say that. I loved him more than any other dog. I don't want Poppy and Maisie to hear me. I love you too, girls. So this is Ben, and Bentley was a reproductive mutant because he had 5 legs. So he was a tripod. You can see here's his 2 little back legs. Here's his 1 front leg. And then over here, he had 2 little chicken wings. But it wasn't like 1 leg divided incorrectly or was created incorrectly. What he ended up having was the bones of 2 separate limbs. Now, he was missing a lot of them. Like he didn't have a humerus and he didn't have a radius ulna. So this whole part of his leg was missing. He did have a metacarpal that kind of came out where his shoulder was. And that's what he had, 1 little toe. And then he had a second metacarpal, had another little toe. So he was my mutant. He was a genetic mutation. Obviously, I don't know if the mutation would have gone into offspring because I did, yeah, take my little hand. He never had the opportunity to reproduce. But he is pretty amazing. He's a pretty great little dog. He loved riding in the Jeep, but he hated the wind in his face. So I got him these doggles, and so he'd hang out in the Jeep and enjoy it. Here's some other genetic mutations. Look at this. You guys are learning all about this right now in behavior class. The difference between this dog, this dog, this dog, and this dog is simply a mutation. And canines have the most slippery, changeable DNA of any other species on the planet. I can take and add and subtract and kind of scramble up the DNA and change the sequence, which is what would give me a brachial cephalic versus a dolichocephalic. The long leggy look of a sighthound versus the short chubby look of a dachshund. It's all just genetic mutations. And as we are manipulating those genetics and developing more and more mutations, that's how we get different breeds. It's also how we manipulate the breeds we have. A great example of a breed genetic manipulation is the Newfoundland, the good old Newf. Newfoundland dogs are genetically modified. Yes, I use the word modified, genetically modified to be water dogs, same as labs. But Newfoundland is genetically modified to seek and rescue. That is not something they have to be taught. It is something that is already ingrained inside of them. Now, obviously, the minutia of the job has to be taught, but you get the idea. Well, here's the problem is, what color are Newfoundlands? Does anyone know what, well, not brown, but it does start with a B.
They're black, right?
They are a black, big, hairy black dog. Well, here's the problem is they're used for open water rescues. What color is the water? Black. So what was happening is in these Newfoundland dogs, couldn't see them. So somebody got the really great idea, although honestly, would it not have been easier just to put a little badge or a coat or a reflector strip on them? Yeah, but somebody decided, hey, let's genetically modify them. And so what they ended up doing was they added a little bit of Great Pyrenees. And what they do is really pretty weird, is they, in true genetic manipulations, they isolate the repeat that gives the Pyrenees its white coat. And they splice that into the Newfoundland. So now the Newfoundland looks like an Oreo cookie. He's got a black head and feet. He has a big white strip down the middle, and he's got a black tail and feet. And these are called Landseers. We renamed the color because you can see them from land. So that's just kind of a fun little story about how we can manipulate genetics. Again, these are reproductive mutations, not cellular, not mitotic, but they're more fun to look at. Here you got a little two-faced kitty. Here you've got a little two-headed baby. And this is a chicken that was found at Chernobyl, which was the nuclear plant, or not the nuclear, the power plant in Chernobyl, Russia, that went down. There's a really fabulous series on HBO if you ever want to take a look. It's terrifying.
So would you just consider cancer to be a lack of contact inhibition?
Yes, cancer is a lack of contact inhibition combined with a manipulated DNA. So let's say one of my liver cells, well, I'm not putting that juju on me. Let's say invisible fake person's liver cell, something has happened, a virus, something that scrambled up the DNA. And now this one liver cell does not understand how to act as a liver cell. He's just like, duh. Well, the problem is he's still replicating, but now he is replicating cells. It's like the movie Idiocracy. You know, this cell, if we want to just anthropomorphize it, the cell is now stupid and it's breeding more stupid cells. And so suddenly I don't have any liver cells that work. But the other problem is that these cells never come in contact with side to side front to back, because until they literally take over my entire body, that would be the only time that they would get contact. So that's why your organ function fails and your tumors grow uncontrollably.
Is chemotherapy changing those or just getting rid of those cells?
Oh, that's a fabulous question. So there's a couple of different types of chemotherapy. And now, Hannah, thank you. We're talking about mitotic mutations inside the DNA of a cell. So the way that chemotherapy works is there's a couple of different drugs. The big grandiose is that it's not very selective. The idea is you get the chemotherapy. Now the chemo is meant to target those specific cells and wipes them all out. But the problem is that any cells that even resemble or look similar are also wiped out. And so you might have certain epithelial cells that were healthy get targeted, which is one of the reasons why you lose your hair. Your hair is just dead epithelial cells. The other problem is that it may target other organ function. So although I'm taking chemotherapy to treat the tumor in my liver, and it's meant to only kill the tumor cells in my liver, guess what, guys? My kidney cells resemble those tumor cells. And so the chemotherapy is going to come in and go, okay, you kidney cells don't look exactly like the guy I'm trying to kill, but close enough, we're going to kill you too. And so that's why you can have other organ failure associated with the chemotherapy. I know. I get very
How does the
excited.
chemotherapy like know to kill those certain cells, even the ones that look similar? Like, how does that chemo know to go for that?
So it has everything to do with the protein, the kind of the, remember we talked about the glycocalyx, which was the sugar protein identifier on the cell. And so how do they get the drug to manipulate only that one cell? That's scientists on a bigger pay grade than me. But what they can do is they can, in fact, program that drug no different than an antibiotic. Okay, we have a bacteria, I breathed it in, but we have, you may have heard gram positive, gram negative. That's just referring to the identifier. And then you have what's called a broad spectrum, which will get both positive and negative, but fewer of both. So if I have a specific bacteria that I know is gram positive based on its protein signature, I can give a drug that will only target gram positive protein signatures. With chemotherapy, though, the problem is that when we program, and that's why there's so many different types of chemo, oral chemo, injectable chemo, and the injectable, there's I don't even know all of the different types, but they're all meant to target a specific protein calyx identifier. But again, how do they do that, Charles? I don't know. They have scientist people far smarter than me that do it. So differentiation just means that we have individual characteristics. You guys, me, we are what we call differentiated. Here's what I kind of mean by that. We are all human. We are all human beings. However, we have our own characteristics and we have our own functions. I am a cell who has curly hair now and brown eyes. And my job as the Huff cell is to be a teacher. You each have your own individual characteristics and your own purpose. That's what we mean by differentiation. My liver cells look and function different than my kidney cells, but they are both classified as cells. Your job and look is different than mine, but we are all classified as people, human beings. And so this differentiation is what allows our different cells to carry out their different functions and keep them focused. And that
Can
is
you go
that.
back?
Oh, sure. I'm so sorry. Let me get back in here. I unshared. There you go. So that's what I mean by differentiate. And differentiation sounds like the word different, which is exactly what we're talking about. Different, but the same. We're still cells. You and me are all cells keeping a being alive. So if our being, if we are all cells making up something bigger, we are all making up this anatomy class. Every single one of us brings something different to the class, but ultimately it's to enhance the class. My liver cells, my kidney cells, my spleen cells all do different roles to keep the class of Huff alive and well.
Thank you.
You are very welcome. So yes, Deanna, radiation has the possibility of creating mitotic disorders, mitotic mutations, and /or genetic reproductive mutations. So not only can it cause your cells to turn into cancer, which would be a mitotic mutation, but it can mess with your reproductive cells and give you a reproductive mutation. Radiation is very super, so really 5G towers, meh. I'm a little bit more concerned about, the radiation I've absorbed over my life, taking radiographs. Although I'm very closely monitored and I'm fine.
You get taken more radiation from the sun than you would do if you were on a nuclear ship.
Yeah, absolutely. Absolutely. You're absorbing more radiation from your computer screen right now.
Bananas, spinach.
Everything. But when you have a massive failure like the Chernobyl failure, that's when you start getting into issues.
Yeah, well, that's
We're actually going to talk a little bit more about, believe it or not, we're going to talk a little bit more about radiation when we get into nutrition next term. We're going to talk about the role of radiation on the thyroid gland and what nutrient can we take to help block the accumulation of radiation in the thyroid. So we're not done talking about radiation. All right, so